Hello everyone. Today we are going to analyze this frame using Stiffness Matrix Method. Before analyzing, let us see the frame one time. In this frame, there are two columns, column AB and column CD. Also, there is a beam BC. In the columns, there are no loads. In the beam BC, there is uniformly distributed load 12 kN per meter. It is acting for the full span. In the point B, there is a nodal point load 6 kN. It is acting towards the right side. The height of the column AB is 4 meter. The height of the column CD is 2 meter. The length of the beam BC is 4 meter. The moment of inertia for the column AB is 4I, for the beam BC it is I, and for the column CD it is 2I. In this frame, the support D is yielding. The vertical displacement in the support D is 4 mm. When we convert 4 mm into meter, we are getting 0.004 meter. And the displacement occurs downwards. The horizontal displacement in the support D is 1 mm. When we convert 1 mm into meter, we are getting 0.001 meter, and the displacement occurs towards right side. The flexural rigidity EI is given as 4000 kN meter square. This frame is a sway type frame. Let us assume that the sway occurs towards the right side. Now let us find the kinematic indeterminacy of the frame. In the joint B, we have the slope theta B. In the joint C, we have the slope theta C. Also, we have the sway. So, the kinematic indeterminacy of the frame is equal to 3. Now let us find the fixed end moments. In the column AB, there is no load, so M of AB and M of BA are 0. Now let us find the fixed end moments in the beam BC. In the beam BC, there is UDL 12 kN per meter. It is acting for the full span. The formulas for the fixed end moments are minus WL square upon 12 and positive WL square upon 12. We know that in the support D, we have vertical displacement 0.004 meter. This displacement will make the point C to come down by 0.004 meter. We just saw that the point C comes down by 0.004 meter. So we have to find the fixed end moments due to the vertical displacement. The formula is 6EI delta upon L square. Since the displacement occurs on the right side, these moments will be negative because they will be acting in the anti-clockwise direction. Let us apply the values inside the formulas. W is 12, L is 4, EI is 4000, delta is 0.004. After the calculations, we are getting M of BC and M of CB. Now let us find the fixed end moments in the column CD. In the column CD, there is no load, so there will be no fixed end moment due to the loads. In the support D, we have the horizontal displacement 0.001 meter towards the right side. So we have to find the fixed end moments due to the horizontal displacement. Since the horizontal displacement occurs towards the right side, the moments due to displacement will be positive. You can see that both of the movements are acting in the clockwise direction. Let us apply the values inside the formulas. Length of the column CD is 2 meter. Delta is 0.001 meter. The moment of inertia for the column CD is 2I. So we have to multiply the EI value with 2. After the calculation, we are getting M of CD and M of DC. Since this is a Sway type frame, we have to find the horizontal reactions in the points B and C due to the fixed end moments and the loads. In the column AB, there are no loads. Also, the fixed end moments are 0. So, the horizontal reaction in the point B will be 0. In the column CD, there are no loads, but we have the fixed end moments due to the displacement. So we have to find the horizontal reaction in the point C due to these two fixed end moments. Let us assume that HC is acting towards the left side. To find HC, let us take moment about D. In this case, we are moving towards right hand side. Clockwise will be positive and anti-clockwise will be negative. HC is acting in the anti-clockwise direction, so it will be negative and the distance is 2 meter. So minus 2 HC. Both of the moments are acting in the clockwise direction, so both of them are positive. Finally, we are getting HC. For HC, we have got a positive value. That means our assumption is correct. HC is acting towards the left side. Now let us make the fully restrained structure. For that, we have to give fixed supports in the points B and C. Now let us make the coordinates diagram. Let us keep the first coordinate in the joint B because in the joint B we have the slope. Let us keep the second coordinate in the joint C because in the joint C also we have the slope. The third coordinate is the sway. Since the sway occurs towards the right side, let us keep the coordinate also towards the right side. Now let us see the formula to find the displacements. Delta matrix is equal to K matrix inverse into P matrix minus PL matrix. In this formula, first let us find the P matrix. In the P matrix, to find P1 and P2, we have to check the first two coordinates whether there are any movements. Our first coordinate is in the point B. In the point B, there is no movement. So P1 will be 0. Now let us look the second coordinate. Our second coordinate is in the point C. In the point C also there is no movement. So P2 is also 0. Our third coordinate is the sway which is acting towards the right side. To find P3, we have to look at the points B and C if there are any horizontal loads. In the point C, there is no horizontal load. In the point B, we have a horizontal load 6 kN. This load is acting towards the right side. Since this load is acting in the coordinate direction, we have to apply 6 as positive. In this formula, now let us find the PL matrix. Let us find P1L. Our first coordinate is in the point B. In the point B, we have calculated two fixed end moments, M of BA and M of BC. We have to add both of them. After adding, we are getting minus 22. Let us find P2L. Our second coordinate is in the point C. In the point C also, we have calculated two fixed end moments, MFCB and MFCD. We have to add both of them. After adding, we are getting 22. Our third coordinate is the sway. To find P3L, we have to add the horizontal reactions HB and HC. We know that the horizontal reaction HB is 0. We have calculated HC. HC is acting towards the left side, but our coordinate is acting towards the right side. Since HC is acting in the opposite direction of the coordinate, we have to apply HC as negative. When we add these two values, we are getting minus 12. In this formula, we have calculated the PL matrix and P matrix. Now we are going to find the stiffness matrix. In the stiffness matrix, now we are going to find these four values. For that, we have to apply unit displacement in the first two coordinates. Then we can use the formulas. If the fair end is fixed, the formula is 4EI upon L. If the fair end is hinged, the formula is 2EI upon L. Now let us find K11 and K12. For that we have to apply unit displacement in the first coordinate. Our first coordinate is in the point B. So in the point B, we have to apply unit displacement. In the point B, there was a fixed support, but when we apply unit displacement, we can assume that it becomes a hinged support. Now let us find K11. For that, from the point B, we have to look other ends. In the end A, there is a fixed support. If the fair end is fixed, the formula is 4EI upon L. Length of BA is 4. Let us apply that. The moment of inertia for BA is 4I. So in the formula, instead of I, we have to apply 4I. Now let us look other end C. In the end C also, there is a fixed support. So we have to apply the same formula 4EI upon L. Length of BC is 4. Let us apply that. For K11, we have to add these two values. After adding, we are getting 5EI. Now let us find K12. For that, from the point C, we have to look other ends. For CD, there is no curve, so no need to look at the end D. Let us look the end B. In the end B, there is a hinged support. If the fair end is hinged, the formula is 2EI upon L. Length of CB is 4. Let us apply that. Finally, for K12, we are getting 0.5 EI. The values of K12 and K21 will be same. Now let us find K22. For that, we have to apply unit displacement in the second coordinate. Our second coordinate is in the point C. So in the point C, we have to apply unit displacement. In the point C, there was a fixed support, but we can assume that when we apply unit displacement, it becomes a hinged support. We have already found K21. Now let us find K22. For that, from the point C, we have to look other ends. In the end B, there is a fixed support. If the fair end is fixed, the formula is 4EI upon L. Length of CB is 4. Let us apply that. Now let us look the other end D. In the point D also, there is a fixed support. So we have to apply the same formula. Length of CD is 2. Let us apply that. The moment of inertia for CD is 2I. So instead of I, we have to apply 2I. For K22, we have to add these two values. After adding, we are getting 5EI. In the stiffness matrix, we have found these four values. Now we are going to find the last row. For that, we have to apply unit displacement in the third coordinate. Our third coordinate is the sway. We have kept our coordinate towards the right side. So towards the right side, we have to apply unit displacement. To find K31, we have to calculate the moment developed due to sway in the point B. The formula to find the moment developed due to sway is 6EI delta upon L square. Since the sway occurs towards the right side, the moments developed due to sway will be negative. For K31 in the formula, let us apply the values. Length of the column AB is 4 meter. Let us apply that. The moment of inertia for AB is 4I. So instead of I, we have to apply 4I. The value of delta is 1. Finally, we are getting K31. The values of K31 and K13 will be same. Now let us find K32. For that, we have to find the moment in the point C. In the formula, let us apply the values. Length of the column CD is 2 meter. Let us apply that. The moment of inertia for CD is 2I. So instead of I, we have to apply 2I. The value of delta is 1. After the calculation, we are getting K32. The values of K32 and K23 will be same. Now let us find K33. For that, we have to find the summation of horizontal reactions in the point B and C. The formula to find the horizontal reaction due to sway is 12EI delta upon L cube. First, let us find HB. Length of BC is 4. The moment of inertia for BC is 4I. So instead of I, we have to apply 4I. The value of delta is 1. For HB, we are getting 0.75 EI. Now let us find HC. Length of CD is 2. Let us apply that. The moment of inertia for CD is 2I. So instead of I, we have to apply 2I. The value of delta is 1. After calculation, we are getting 3EI. For K33, we have to add these two values. After adding, we are getting 3.75 EI. Both of these reactions will be acting towards the right side. Our coordinate is also acting towards the right side. Since these reactions are acting in the coordinate direction, K33 will be positive. In the stiffness matrix, we have calculated all of the values. Let us enter them. Let us keep EI outside. In this formula, we have found everything. Let us apply them. EI inverse is 1 upon EI. For this matrix, we have to find the inverse. We can apply all of the values in the calculator and get the inverse. If you do not know how to find inverse in the calculator, see the description below. There is a link. You can click the link and watch the video. I have used the calculator and got the inverse. Then we have to multiply these two matrices. After multiplying, we are getting the displacements. Now let us make the slope deflection equations and find the final moments. First, let us make them in the column AB. Since the column AB is subjected to sway, with the equation we have to add the sway moment. Since the sway occurs towards the right side, the sway moment will be negative. Let us apply the fixed end moment. Length of AB is 4. Let us apply that. The moment of inertia for AB is 4I. So instead of I, we have to apply 4I. In the point A, we have fixed support. So theta A will be 0. After applying the values of theta B and delta, we are getting MAB. In the similar way, we can find MBA. Now let us make the slope deflection equations in the beam BC. In the equations, first let us apply the fixed end moments. Length of BC is 4. Let us apply that. After applying the values of theta B and theta C, we are getting MBC and MCB. Now let us make the slope deflection equations in the column CD. Since the column CD is subjected to sway, with the equations we have to add the sway moments. First, let us apply the fixed end moment. Length of CD is 2. Let us apply that. The moment of inertia for CD is 2I. So instead of I, we have to apply 2I. In the point D, we have a fixed support. So theta D will be 0. After applying the values of theta C and delta, we are getting MCD. In the similar way, we can find MDC. In this analysis, we have calculated all of the moments. Now we are going to find the reactions. First, let us take the column AB and find the reactions. When we take moment about B, we are getting HA. When we apply this rule, we are getting HB. Now let us take the beam BC and find the reactions. When we take moment about C, we are getting VB, and when we apply this rule, we are getting VC. Now let us find the reactions in the column CD. When we take moment about D, we are getting HC, and when we apply this rule, we are getting HD. Using the reactions and loads, we can draw the shear force diagram. Using this formula, we can draw the free movement diagram. Using the direction of the movements, we can draw the end movement diagram. Then we can combine both of the diagrams and draw the bending moment diagram. Alternatively, we can draw the bending moment diagram on the tension side. In the beam BC, here we have the maximum positive bending moment. Let us see how to find the point where the maximum positive bending moment occurs. Let us take the shear force diagram. In this point, the shear force becomes 0. In this point, there will be maximum positive bending moment. Let us make a section in that point. We know that in this section, the shear force is 0. Using that concept, we can find x. Using the value of x, we can find the maximum positive bending moment. Now we are going to end this session. Thank you for watching this video.